I can't talk and write right now, so just let me write and then I'll talk. I don't know why. It seems like I'm just done it when I get to your class. I'm just done. You all done? You should just call it a day. Yeah.
That's good.
Talk about like the protozoa.
Okay. So this is the outline for today. We're going to talk about aryl diazonium salts. Aryl diazonium salts are very nice because they allow us to get other things on the ring that we, to this point in time, don't know how to do, right? So when we make these beautiful reaction webs, right, we have all this ability to create these nice things, but there's a few things we haven't learned how to get on there, like a cyano group, or an iodo group, or even a hydrogen to remove a group, which would be nice as well. So this is what the aryl diazonium salt usage is for. So that's to sort of swap out. Now the swap out always comes from a nitro position. You can't swap out anything unless you have a nitro at that position to begin with. So it does require that you create nitrobenzene and then work from there. Okay, so we'll be talking about those reactions. These last two categories fall into this nucleophilic aromatic substitution. That's what this NAS is, right? It's nucleophilic aromatic substitution. So as always, aromatics undergo substitution as opposed to addition because substitution allows them to maintain aromaticity, and addition, they lose aromaticity in doing it. The nucleophilic aromatic substitution means that the ring is behaving as an electrophile, okay? Behaving as an electrophile. And so there has to be a good leaving group on the ring, right? There has to be a good leaving group because that's usually the electrophilic center, right? What have you learned about substitution other than it occurs at centers that contain good leaving groups? Generally, these are brominated positions. Br is a good leaving group. As you climb the category Cl, F, they become actually worse leaving groups. That's just, Br seems to be the happy medium. So generally you see these from brominated complexes, okay? So we're going to switch the tide there. So to start from the top here, the first thing to do, I guess, is just to create a chart of how to get to an aryl diazonium salt and what it is and why it's useful. So like I said, you have to start from a nitrobenzene. And once you have a nitrobenzene on here, you know that you can reduce this to aniline. Aniline is actually the starting point for creation of the aryl diazonium salt. Okay? So the first step is to add something like NaNO2, generally added with some HCl present. This gives me, at first, sort of a nitrosyl group. You guys have all heard of nitrosyl groups. Does anyone know where nitrosyl groups can be found, that NO group? Bacon, right? Or know about bacon? How it's really bad for you? That's why, because of the NO group. Regardless, that does a lot of redox chemistry in vivo in your body, which is not supposed to be good for you, but I think everything in moderation is just fine. So, not that this is a dietetics class or anything like that, I'm just saying. It does start from this nitrosyl addition to aniline, which means you need to have aniline alone, okay? You can't actually have a secondary amine or a tertiary amine. There has to be two hydrogens off of that nitrogen group, which really means that you can't now go do some substitution here and make a methyl group off of it and still come around to create our aryl diazonium salts. This is an intermediate along the path. We haven't gotten there, but I just want you to note that you have to have a primary amine in order for this reaction to happen. So this is step one, right? Step two is actually HCl generated, and what it actually creates is nitrogen gas on the ring. And nitrogen gas on the ring now is probably the best leaving group that we can have, right? Because it's semi-attached to the ring here, but it's making for a great slot replacement here, right? I mean, this is primed to go, and what do you know about gases in general? Gases are fantastic leaving groups. You can't have a better leaving group because they leave and they're gone, right? They bubble out of solution and they're disappeared. They're never coming back. That's the best leaving group that we can have, right? A lot of times leaving groups sit around in the pot and they could come back and they could react, but gases are totally gone. So this creates nitrogen gas attached to the ring and allows for lots of different substitutions to be made here. I'm only going to highlight a few, but there's probably about 20. If we really want to go, you can come up with about 20 or so reactions, and even more, I'm sure, if we scan the primary literature, which we're not going to do. But one is this CuCN, which allows us to create now a cyano group on the ring. This nitrile, the cyano group, nitrile, belongs in the carboxylic acid family member sort of population. So this is a good way to get into this carboxylic acid family if we want it. Okay, so that's why this is going to be useful to us in the future, is that it gets us into this derivative family, which we may, in essence, want to be creating something off the ring here that has some of that reaction chemistry. Another thing that it can do is it can put these other groups on the rings, which you don't know. For instance, you can add an iodo. So copper iodide will add an iodo group. Okay. HBF4 adds a fluoro group, fluoro. So that's also very useful. And the last one, which I think is useful, and like I said, you can go and study a whole bunch, is H3PO2, which in essence now completely removes that slot. So you can fill it, use it as a director, bring it down to an aryl diazonium salt, and then remove it. That's very nice, right? What is the other group that you know you can add and remove and use it as a director?
Sulfate.
Sulfonation. Great. Okay. So this here is our aryl diazonium salt. And if you want, you can sort of work through the mechanism. It's a good thinking mechanism. I'm not going to do it in class today, but it's a good thinking mechanism, okay? Because when you get to this spot right here, and you add HCl, what do you think is going to happen?
The gas gonna leave.
What happens when you have any acid in a flask with oxygens and nitrogens? What happens to them?
Water.
Water can be created, right? And this is a nice one to work through to see if you can think through the mechanism. It allows you to see if you can think on your feet, right? Try it, attempt it. It's a good one to attempt because you know what you're driving to, okay? You're driving to the loss of water because when you lose water, what do you have left but two nitrogens, right? In a triple bond or nitrogen gas. So this is a good thinking mechanism. We're going to be doing a lot of this type of thing moving on. So I'm going to leave this here. It's on the weekly quiz as promised. The answers are coming out today for the weekly quiz, so you have the answer if you decide to work through it. Okay? Are there questions about aryl diazonium salts? Yes?
Why are we using copper?
Why are you using copper? You know, that's a really good question. And the question that the next question, right, could be, why can't you use other metals? It's a very interesting question. Copper is, +1, iodo is -1. I don't know if sodium iodide would work as well. Copper might have special properties it brings with it. I'm not really quite clear. But I know, even back in my, day, it was always copper iodide. But I've never done this reaction in the lab, so I can't really ascertain why that might be. I've never thought beyond that. Okay, so what's the use of these aryl diazonium salts, we said? Someone give me back, in summary, what are a couple good uses of these? Okay, I don't understand all that mumbling. Someone's going to have to raise their hand, or we can get the UMEG list up here, and I'll start calling people at random. That'll be fun, right? Does that scare you? Yes?
You can get things onto the ring.
You can get things onto the ring that you don't yet know how to do, right? All these three reactions, cyano, iodo, fluoro, you don't know a reaction to get those on the ring. So this is a way to get things on the ring that you don't yet know how. So if you see this on an exam, if you see one of these on a ring on the exam, what did you go through? An aryl diazonium salt, right? So let's be very clear. If I were to say, have something something like this, what would you write out in succession, right? What would you write out in succession to get from my starting benzene to iodobenzene? First, you need
Yeah.
HNO3 with H2SO4. Great. Second, you need
HCl.
10 HCl. Great. Third, you need HCl. That's right. That's really all. I mean, my point was the HCl was going to do this last piece. So this is really all you need to get to the aryl diazonium salt. Last step, copper iodide, not sodium. Okay, so this is what you would write in order to get there. So yes, number one, it gets things on the ring that you don't know how. In succession, this is what you'd want to add. What is another potential good thing for aryl diazonium salts?
Can you remove a hydrogen?
You can remove the nitro group in place of a hydrogen, right? So you can use that nitro group as a director, right? So you can direct something onto the ring and then remove that nitro group after the fact, okay? So that is also the second thing that I was trying to get you to say back to me about these. Yeah?
So if you're using it to direct something onto the ring, are you doing it for the purpose of putting it at a meta position?
Yes, I am doing it purposely to add things meta to one another that may, once upon a time, wanted to go ortho-para. We have a little reaction web at the end that you'll see this in action. So if you can just hold that, yeah.
If you're going to remove where the NO2 was anyway, then it wouldn't be meta anymore.
No, it would. Because if I say took this and I added two things, right? Let's just say I added two things. And the first thing I add, say, is meta as well, right? Not to say this is a halogen, maybe I should do Y, right? Okay, so if I do this and I add a second thing, now they're meta. If this goes, these are still meta, right? So yeah.
Do we have to worry about any of these reacting with the other stuff that are not NO2?
Okay, there's very little, the one thing that I would worry about reacting are things like phenols. OHs are a little bit finicky. We likely will let it go if you're doing a synthetic scheme on the exam. We're likely to let it go. But phenols are really one of the most finicky things that we have. But past that, no, there's very little that you're going to have to worry about in here. Yeah, it's a great question. Sorry.
That synthesis over there,
Yeah.
you have Na, NO2,
Yes.
and HCl. On your mechanism, you have HCl after that.
Yes, that's just to say that the HCl continues to go there, is really what it is. Really all you have to do is add NaNO2, HCl. It's usually run at low temperature. We're not going to hit you on that one. There's a lot of things that can be run at low and high, and I want to sort of be directed in those. Okay, great. So aryl diazonium salt's very useful. Now, the latter two come into this nucleophilic aromatic substitution. So, I said on the notes, right, in your homework, there was a question about which one of these rings is going to undergo electrophilic aromatic substitution fastest, right? It would be the opposite for nucleophilic aromatic substitution, right? Because in nucleophilic aromatic substitution, generally you have a benzene that has minimally a leaving group on it, okay? A leaving group on it like Br. And what you're trying to capitalize on here is the fact that this site here, the carbon on the ring that the Br is attached to, you're trying to capitalize on that being electrophilic. So if I start sticking electron donating groups on here, right, that push electron density into the ring, right, they're in essence going to swamp out that partial positive charge that you're trying to build up, right? So an electron with donating group is bad. So electron donating groups are bad when we're talking about this. We prefer to have electron withdrawing groups on here. So if I added something like a nitro group, this pulls electron density itself and hence maintains now the electrophilic nature of the ring. So for nucleophilic aromatic substitution, those deactivators are best, right? So those would include the halogens, all of our carbonyl species where it's actually the carbonyl carbon that's attached, and then our nitros or sulfonyls, etc. Okay? First and foremost, does that make sense? Are there questions about this? Because this is important criterion. All right, so there's two types of mechanisms that we can talk about when we talk about nucleophilic aromatic substitution. One of them is to start from bromobenzene alone, okay? But these are hard to work with. They're hard to sort of make happen. So let's talk about those first. That's actually category 3. So if I wanted to start with bromobenzene alone, the only place that on the board I can see all this other random stuff that I have no idea what it means. Like this says improv George Marty. I don't even know what that means. Usually it's chemistry behind, and I'm like, oh look, they were doing acid-base chemistry or something, right? This I'm always like, who the heck are these people? Okay, so if I start with bromobenzene, this proceeds through a benzyne intermediate. Zyne, Z-Y-N-E. What does the Y-N imply?
Alkyl
A
line.
triple bond, right? Exactly. Okay, so one base that is sure to go here is sodium amide. Sodium amide is a very good base, generally delivered in its conjugate acid as a solvent. Bases are generally delivered in their conjugate acid as a solvent. You've seen that many times before. But NH2- is a strong enough base to make this reaction happen. Okay? You don't generally need to heat it up very much. It's going to happen as is. All right? And this is what happens. We skip the counterion here, which spectates the whole time, and you actually see now the pole of a beta hydrogen. A hydrogen off the carbon next to the leaving group, right? And as you've seen before, in an E2 type fashion, it's going to donate its electrons back toward the leaving group, and the leaving group is going to be removed. Now this intermediate, I use my little quotations, is very hard to sort of capture and bottle, right? Anything that's relatively unstable, you can't actually stick in a bottle and put it on your shelf as like a wonderful prize, right? This is actually something that is fleeting, so we're not going to call it a transition state, but I am going to bracket it as if it's not something that's going to stick around. Now, why would this intermediate stick around?
It's linear.
Because of the sp nature of the ring, right? I have 2 sp carbons in the ring. This is not something that can stick around. You're trying to maintain the ring structure, the cyclic structure. That can't happen when it's sitting around. So what actually happens here then is that your amine comes and attacks at one of these sp centers. Yes?
The other double bonds go away?
No.
Okay.
Thank you. So in this case, this is where counterintuitive sort of comes in, because it's a nucleophile after sort of a nucleophile, right? So this is a little bit of trouble, but this NH2 group can come and attack either sp carbon. Now it doesn't matter in this example, because if it attacks one site or attacks the other, you're still just getting aniline. That's all you're getting out of it. But I do want you to note that it can attack either center, okay? And that might lead to different constitutional isomers. So you should be aware that it can attack at either center. In essence, though, this is the reaction as it happens. And as it comes in and attacks, an electron pair is being pushed away, and the electron pair is going to be captured by ammonia. So its conjugate acid is going to serve to create now this hydrogen, or to take a hydrogen, and thus now regenerate the aromaticity. And in place of the Br, there is now this nitrogen species. Okay? Now, as you change this base, you change the ability for this reaction to really work the way that it's meant to. If you bulk up the base, meaning I add some R groups off of it, it can work, especially if you stick to the nitrogen group. However, when you work down to say something that you also consider a good base, like NaOH, NaOH is not going to do this at room temperature. It's not. It requires more reactivity. So what we actually do is we heat it up. We make it easier to go. NH2 minus will work as is, okay? But any oxygen base that you want to do this with, so say NaOH or NaOCH3 or NaOT or ET, NaOET, right? Anything like this requires heat. And this is somewhere where we will mark you off if it's missing. Mainly because there's a big distinction here in terms of being able to create this benzyne intermediate. It's not something that's going to happen willy-nilly because of the physicality of creating a triple bond within this cyclic structure. If you heat it up, though, generally you can see some substitution happen. But you got to be careful when you heat anything up because lots of stuff can happen in other places on your ring. Whenever you now put in base with some heat, you're guaranteeing that other things are going to be happening in there as well. Does everyone see what I mean about the distinction here between NH2 minus and OH minus? Everyone sees them as drastically different bases, right? Let's be very dramatic here. They are drastically different bases. NH2 minus is derived from NH3. pKa is, that's right, it's 36. OH minus is derived from H2O. pKa is,
15.
good job, 16. 36 and 16. 20 orders of magnitude, right? Each pKa unit is an order of magnitude. Very big difference. Definitely a necessity.
So do you not need nitration then to make the aryl diazonium salt?
You can go through this. As long as you have an NH2, you now can work through. That's exactly right. Before we didn't know another reaction, but absolutely. You can now, right, skip this step and go right to aniline if you need it. Yes. Uh-huh.
I was just wondering, where do you draw the distinction, pKa-wise, of like a strong base? Because I know like NaH is even stronger, but would you ever use NaH?
No, we don't generally use NaH. Hydros are very, very finicky nucleophiles. I can't really think of another base that you want to add, which means there is no test question on that, if that's where we're going with this. Because sometimes that is where we're going. But I'll put some thought into that. Yes?
So you just said that this can replace the nitration first.
Yes.
But for this case, you first have to brominate.
Yes, you do. That's exactly right. You would need to brominate and then run a reaction with NH2 minus. That's exactly right. So you're still a two-stepper, right? But point taken, yes. The only requirement to get to an aryl diazonium salt is that you start with aniline. So if you can get to aniline, of which this is a secondary way to get there, you're good to go. Great question. Okay, so the last one, 2 here on our board, is something called a Meisenheimer complex. It's still a nucleophilic aromatic substitution. I don't know if it's not called the Meisenheimer reaction. Maybe people do call it that colloquially, but it proceeds through a Meisenheimer complex. And a Meisenheimer complex actually makes these reactions easier. Here's why, okay? If I take my bromobenzene and I change it ever so slightly, question is, has this made the ring more or less electrophilic? What is my change? My change is
Meta
versus para, but let's back up. Generally, it's the addition of a nitro group, right? And the nitro group, is this going to make nucleophilic aromatic substitution easier or harder?
Easier.
Easier. Okay, so number 1, it's certainly doing that. The Meisenheimer complex is the addition of nitro groups to specific positions, which you're going to tell me which in a minute. If you know the answer beforehand, you're going to do it my way anyway, because I say. Now, in this case, you are talking about, what I want to say is, if you had other electron withdrawing groups on the ring, great. That can make it go even faster. But the Meisenheimer complex alone is about specific placement of a nitro group. So I'm going to work through one, or I'm going to show you one, and then you're going to work through the other. We're going to break for 2 or 3 minutes, and you're going to attempt this on your own, and we're going to see what happens. Now I'm just making this a little bit more correct in terms of all placement of groups here. Okay, so here we go. I'm going to add a base. Note, because I've now put this nitro group on the ring, I don't have to worry so much about the heating issue, right? I can pretty much use generic bases, even like a hydroxyl group. So here we go. We're going to take this, and it's going to attack at this position. This is like an SN2. The benzyme was like an E2, right? This is looking very SN2 in nature, okay? So here we go. This is one potential intermediate, once I get my second arrow in, that I see attack at that carbon center. Always the carbon center the halogen is attached to. That's what SN2 does, right? It heads right into that alpha site. That alpha site can't take 5 bonds, so it gives up a bond. In this case, it's giving up pi electrons. We get one intermediate, okay? You're going to work ahead of me, and you're going to draw all the intermediates that exist for this addition. And then we're going to switch, and we're going to do the same thing for this other molecule. And in the end, you're going to tell me the answer. Based on what we have on the board, you're going to tell me the favored placement for a nitro group, why that is, okay? So here's our dividing line. I'm going to draw the resonance structures moving left for the meta placement of the nitro group. Then I'm going to come back and do it for the para placement, and you're going to work ahead of me to make sure that you can draw the resonance structures. Yeah?
Is it always going to add to the carbon that's closer to the nitro group?
It's always going to add to the carbon the halogen is attached to. Regardless of where the halogen is on the ring, that is the site that the base will always attack.
I was just wondering, because if the bonds were shown the other way...
You can do it the other way too. It doesn't matter, because the benzene can exist either with a bond situated this way or the other way. I just randomly chose this way. I wonder if I have a preference for this. Does anyone... We should do an analysis like this in the notes. How many times do I draw the double bonds this way compared to the other way?
Almost always
To be
like
a good
this.
scientific analysis. No? Scientific analyses are very interesting. Did anyone hear what's the optimum number of days ahead of a flight where you get the best price for an airline ticket? Anyone hear this?
90 days.
Not 90 days.
It's like 3 days.
9. Yep. 6 weeks. No, what does that work out to be? Hold on. 7 times 42. Nope. Guess again. Close. 54. That's awesome. But isn't that amazing? Look at how random is that? That's the most random thing ever, right? But that's scientific analysis for you. It's numbers analysis. Anyway, go ahead. Resonance.
That's great.
I'm not really sure. Sorry.
All right, that should have been time for 3 resonance structures on the left. Do you get them? All right, move to the right. Let's go. Work ahead of me. Be fast. You gotta be fluent. All right, this is it. If you're about a minute behind me or 2 minutes behind me, that's not bad. If you're like 5 or 10 minutes behind me, you got some work to do. I'm not trying to scare you. I'm not trying to intimidate you. I'm trying to make you ready. That's all. I really am not, I promise. So what's the answer? Para. So that would correspondingly mean what as well? Ortho. Because ortho and para go together, right? Ortho and para go together. The requirement to proceed through a Meisenheimer complex, the requirement to proceed through a Meisenheimer complex is an ortho or para nitro group. Certainly, the more the merrier, right? By one ortho nitro group, great. If I have 2 ortho nitro groups, even better. If I have 2 ortho nitro groups and correspondingly a para nitro group, great, right? Does everyone understand what I mean by this? Yes? Okay, so OP. So this is a no, right? This is a big fat no. This isn't going to happen through a Meisenheimer complex, okay? It's not going to happen through a Meisenheimer complex. And really, if you were to look this up online, really the only intermediate they show is this one. This is the only intermediate they really show because that's the distinction. That's the point of distinction, okay? The fact that electron pair can be pushed out onto that nitro group is indeed the point of distinction, okay? So it's from this intermediate that you generally see the latter half of the mechanism, and the latter half of the mechanism is pushing back. Put away the phone. I'm more interesting than that phone, I guarantee you, at least for 50 minutes a day, Monday, Wednesday, and Friday. You can have your noon hour on Tuesday and Thursday. In this case, it's the pushback of electrons toward the leaving group, starting all the way out at the oxygen, coming on in. It can come in either way, right? And in essence, pushes out the leaving group. Br is always, if you've chosen your reaction correctly, the better leaving group, right? Because Br is pretty good at being stable on its own. It's a great leaving group. Okay? So the outcome then is substitution of that OH at the exact position that Br was attached to. Okay? At that exact position that Br was attached to. All right. So let's go back to our starting point here. We've already gone over and reminded ourselves of the importance of the aryl diazonium salts. So let's just come through here and make sure we understand our nucleophilic aromatic substitutions, similarities and differences. Okay, in what ways are these two reactions similar?
The attack.
Okay, you need to have a bromine on the ring, right? So you have to have at least a Br on your ring, right? You need to start with a bromobenzene. It could be a substituted bromobenzene, right? But there has to be a Br on it, because that's the leaving group, right? Okay. How else are they similar?
Can it be like an iodo group or a...
An iodo group is a very interesting case. The iodo group, I don't know if you've ever heard this, and there's only one person in this room who had me, I think, for 231. At least I think that. Anyone else have me for 231? Anyone else out there? No, I think it's just one. I know who you are. So I tell this story in my 231 class about the iodo group. You know, the iodo group is a good leaving group, but it's also a good nucleophile. You know what makes it a good nucleophile? It's squishy. Okay, it's squishy. That's what we would call it. It's a nice, you know the difference, this is my analogy is pillows. My husband and I sleep on very different pillows. My pillow is like one of those like foam type of pillows. It's not a memory pillow, but you know what I mean? Like you push on it, you let go, and it springs back up. But his pillow is a feather pillow, so like he can like mold it. So I joke that his pillow is always the last one we pack in the car because it can make its way into any crevice whatsoever because he's had the darn thing for, and some of you might think this is quite disgusting, I fully contend with this, since I've known him, which is since 1990.
Oh my God.
Isn't that impressive? I make him double pillowcasing now. Isn't that crazy? So that's the pillow story. It's squishy. The iodo group is not a good one. It's not a good one to go with because the iodo group is a good leaving group, but it's also a good nucleophile. So we're trying to get to the medium end of that category. Fluorine is definitely bad because it's not a good leaving group at all. Br and Cl are sort of the intermediates. Br is sort of the one of choice, the winner. Okay, similarities. Br on the ring. What else are similarities? Electron donating groups or electron withdrawing groups?
Electron withdrawing.
Okay, electron withdrawing groups are best. Okay, how are they different?
The intermediate.
The intermediate is different, right? Sort of like E2 versus SN2, right? So we have different intermediates, absolutely. What else? The Meisenheimer complex requires, right?
Resonance.
Requires
Orthopara.
at least an O or OP, right, of some variety, OP nitro groups. Not a requirement for the benzyne intermediate, right? Not a requirement. The Meisenheimer complex can pretty much use any base, whereas the benzyne intermediate is finicky, right? The amine, the sodium amide works at H2 minus, but other bases require heat. Never good to heat a base. I mean, a base is bad to begin with, right? Heat a base, that's even worse. All right?
Why?
And the last one I can tell you is one that you might not see right away. Okay? And I don't know how I'm going to get in that little space, so I'm going to say it out loud. Here's the last one. Okay? The Meisenheimer complex puts the base exactly where the halogen was. But the benzyne intermediate didn't do that, right? It could put it on that exact site or one site over, right? Does everyone remember when we got down to that benzyne intermediate and we were looking at it, I said, so say I had something on here, I said that now it can attack here or here. So if I had this toluene to work with, right, you're definitely getting two different constitutional isomers. Okay, so this benzyme can attack at either sp carbon, which means the site the halogen was on, and the neighboring site, whereas the Meisenheimer complex goes right on that carbon. Okay, does everyone understand that? All right, so let's try a reaction web. I'm going to get this writing on the board, and you're going to start disseminating this. Kim, do you want to come up and help? Ready? You're going to get it in the head.
Yay, go first.
Good catch. Or just passing it back.
All right.
Yay!
Yeah, some in the back and some in the middle here.
Professor? Dr. Dixon? Is there any point where you have to worry about like inversion? I know it's like a benzo ring again. Okay.
No, because you're always off the best in 2 seconds.
Yeah, just checking.
You asked this last week too, do you remember?
I know, but it's a different case, so I just want to make sure. Yeah.
Do you remember that?
Yeah, I do.
Was that Rhea? What letter is this?
Really great.
I did not get it to work to save my life.
What were you trying to do with it?
I was trying to set up a synthesis problem and like create intermediates and stuff like that, and it wouldn't let me do intermediates.
Wait, what are you doing?
I just gave up. Like I got so frustrated. I just
It's really
exited out.
easy, actually, after you figure it out.
Because you know the first synthesis she gave us, I was trying to create like flashcards, but like on key, and I was trying to like type up the whole thing on there, but it wasn't working.
I'll show you how to do it. It's actually really easy. And then you can get Ketamine Biodrop for free.
I got that too. I
It works the
gave up
same
on my
way.
reviews and I went over to that
It
one.
works the same way. I don't know if it can predict amount
Okay,
and
this
stuff
is some
though.
of it.
I don't think it does.
I really started with everything but I, but then I thought I would be wasting paper if I left all that space there blank. And really I got upset that there's also some wasted space on here. I mean, I could have made it harder. But how many is this I? What's I? 9? Is that right? Is I 9? Okay, in the alphabet, you know what? Okay.
Yeah.
So this is like an exam level. 9 slots. This is exactly what your exam. Not exactly. I mean, if I say that, then you're going to be like, you said exactly. But this is similar to your exam. This is what I call reaction web, right? The webs have letters either over the arrows, which means that's a synthetic scheme, or as a product of a given reaction, and that's where you write a product. The products boxes are all squares, and the synthetic boxes are all rectangles, okay? But there's about 9 of the letters, I think. I think we go to J. So 10 letters on your exam. That's about 40 points on your exam right there. Okay, so a web like this. Now this web is, I don't want to say singularly focused, but it is focused in a lot of ways on the use of nucleophilic aromatic substitution and the use of aryl diazonium salts. This particular web today, because I'm trying to sell the point of nucleophilic aromatic substitution and aryl diazonium salts. So I would expect that your web on your exam would be sort of a little bit more equally sort of weighted in terms of electrophilic aromatic substitution, nucleophilic aromatic substitution, and then the stuff on the conjugated systems, right? Diels-Alder, etc. Yeah?
That's going to be on ELMS, correct?
This will be on, yes, I will put this on ELMS and I'll put the answers on ELMS as well. So this is a good start. Okay, so let us come down, because I want you to work through some of it, but I do want to work through just a couple of things with you, and then you're going to do this. I'll get the answers up there tonight so that you can work through this, okay? And I do go back to my office after this. I'm there until about 3 today, and barring that the sun comes out, I'm going on a nice long run today, so I'm out to go running. You're welcome to run with me, but that's a requirement. So you have to run and we'll talk chemistry at the same time.
That sounds miserable.
So in this case, I want to focus first here,
It's like punishment.
okay? The question is, will that reaction do nucleophilic aromatic substitution? NaOCH3, so I knock off the Na, and I think of OCH3 minus. And I know that's a base, and that looks like a good nucleophile, and it looks like a base that's used in nucleophilic aromatic substitution. So I have to hone in at a site that has a bromo group, right? So I come right here, and I say, okay, is it going to do this? The answer is, does it need heat? No. No heat is needed for this reaction, and you're absolutely going, what letter is this out here? C. Thank you. So C looks like this. It's going to be the nitro group. Now an OCH3, exactly where that is, and your corresponding acyl group out here. Okay? No heat is needed. Why did this do a displacement for the halogen? Why? Because of the Meisenheimer, and that nitro group is appropriately placed. It is para with respect to the halogen, right? The requirement is for it to be ortho or para. Okay, how about down here? Is this reaction here What letter am I on down here?
Oh.
I'm on G.
It's meta.
Is this going to go proceed through a Meisenheimer complex?
No.
No. And so the question is, will it do a benzyne intermediate? And the answer is?
Yes.
No.
And why is it going to do a benzyne? No heat. So this is a no reaction. Okay?
I don't know what it's supposed to be.
This is a no reaction. Does everyone see why that is? There are questions about that. Okay. My last, what time is it? You have a time check?
12:48.
Okay. B. Last one I want to do is B. How can B be done? B is right up here on my board. This is B.
Aryl disodium salts.
What do we see between the difference between the reactants and products of B?
Nitro group and
The nitro
The
group.
nitro group is gone. What's a requirement?
Aerodisodium salts.
The aryl diazonium salt, right? Using H3PO2 in the end, right? That's a requirement to make that happen. What else is different?
H3PO 2 or 3?
Okay, we've reduced the ketone, and you all like to use the Clemmensen reduction, which is totally fine and actually safe given what's on the ring currently. We're not going to ding you on that either. I'm just saying it is perhaps safe here. Okay? So you're going to practice this web, and you're going to be ready to come to class on Wednesday.
Like
We'll be
what was it?
reviewing
It
with
reduces
clickers.
the
Do not
ketone. What
forget
would
your
you
clicker
use?
on
I think it's with
Wednesday. Not a
um,
good thing.
is it copper and